11 to 1. Let's pick up some things. I sent you a bunch of videos. A lot of what I planned to cover, I sent you in videos, and basically everything that I'm going to ask you in any way on the exam is now in your hands. So I'm going to fill up some, I'd say giggles and grins, but interesting applications. I talked about the compound nucleus in your notes, and I talked about threshold reactions, and I want to cover a little bit more of that, and then I want to go talk about stars and how stars get their energy, and stars produce all the matter that exists in the universe. And then from there I'll go to fusion as much as I have time, and then I'll finish it out with accelerators and nuclear weapons on Wednesday.
So the material in the videos and all those notes you sent us, that will be on the exam as well?
Stuff on radioactive decay is essentially on the exam.
Okay, but not necessarily all the extra material?
No, I didn't put anything. I'll tell you what I didn't put. I didn't put anything on nuclear reactions.
Okay.
All right, I stopped with what we were talking about decay, but ideas of activity and isobaric decay, that's fair game.
Okay.
Alpha decay is fair game. All right. So I said there were these threshold reactions. Let's talk just quickly about this idea of a compound nucleus. If you're below about 500 MeV, then the predominant way in which nuclei interact is that they come together and the nucleons, if you want, kind of bounce around inside the nucleus. And they undergo many, many scattering operations in which they bang into each other. And so any information about how they were formed or where they came from is kind of lost. So you have this guy kind of like this. Comes in, maybe this is a proton, and maybe this is a nitrogen 15. And from that, he forms an oxygen 16 nucleus. And that nucleus actually stays there for quite a while, and in the process, these protons and neutrons start banging around. And so the fact that he came in this direction is lost. How do we know that? Well, we can put detectors around here, in various places. And we can measure the probability of the cross-section as a function of the angle. And what we find out is whether you shoot him in like this or shoot him in like that or whatever, doesn't make any difference. He's completely lost the information. Kind of like pouring water into a bathtub. And any information about whether you poured the water in from 2 meters high or 1 meter high, or whether you poured it in drop by drop or you poured it in all as a cup, it's all been lost into the banging of the molecules inside. When this happens, this thing that it forms is called a compound nucleus. Now, it was smacked. So there's usually a star indicating this thing is excited. If I took a piece of 2x4 and hit you in the head and stuck it in your head, you'd be excited about it too. All right, you might get upset. And so the nucleus gets upset, and it's got some extra energy, and it'll want to get rid of that energy. Now, it can do it many ways. It could just emit a gamma ray. If it did that, this would be called a P gamma reaction. And in fact, it would look something like this if you wrote the formula. The thing coming in is written first, then a parentheses, then the target. Usually you wouldn't put the proton number, but somebody might. Then whatever came out. Well, the only thing that's coming out of this thing is a gamma plus an oxygen 16. Notice the heaviest daughter is put on the outside, and any other products that come are put on the inside. So if this thing knocked an alpha out, you put an alpha in here. In this case, if it just emitted a gamma, this would be the reaction. And that's one possible actual consequence of this. If you did this at a particular energy, this is one thing that could happen. There are other things that could happen though. Depending on the energy, I happen to know this because I use this reaction, you might get this thing happen. It comes in and it still forms this oxygen 16. But very quickly, almost immediately, this oxygen-16 breaks apart. And it emits an alpha particle, and it emits a carbon-12. And this carbon-12 is still excited, so a little while later it emits a gamma ray. And how do we know that? Because those gamma rays are like fingerprints, like atomic physics. They're energy levels. We can measure the energy of that, and we know that it comes from the carbon, not from the oxygen. It doesn't match the oxygen energy levels. This reaction actually is very useful. It's useful for profiling nitrogen in particular materials. Or if you shoot nitrogen into protons, it is extremely useful for measuring hydrogen in electronic materials for the semiconductor industry. This one has no application purpose. Why not? Well, because of what they do. They both form compound nucleuses, but they don't behave the same way. So in my notes, I talked about you form a compound nucleus and you can have threshold reactions. These are reactions that have negative Q values, and so until you give it enough energy, it never happens. And then all of a sudden, it happens. So if you look at those type of reactions, and you look at their probabilities, called their cross-sections, they look kind of like this. Nothing, 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 nothing. Right there, it's the threshold reaction. They're useful for things like calibration. Let's say you build an accelerator and you have no idea what energy the accelerator is. All you know is that you're supposed to put a certain amount of voltage on it. Well, you can't use a voltmeter to measure the voltage because the voltage might be at 3 million volts. And voltmeters don't work at 3 million volts. So you have to have some way to guess the energy. Now, one way would be to run a bunch of resistors or run current down it. But that'll only work V equal IR if you know the R. And the R of most materials changes if you put it under high voltage. So what they measure on an ohm meter at low voltage is not what it is at high. This is a way to do this. You could run this thing up to this point, measure the energy, and from that determine the voltage. Then take the current that you measured, divide by I, and you got the resistance. And now you can use that to calibrate all your dials. Another way is to generate what they call a generating voltmeter. This is a set of plates that measures capacitance. Same thing though, the capacitance depends on the gas in the machine and so forth. So they usually need some sort of reaction that is calibrated in order to calibrate a system. Now, there are other reactions. So these are thresholds. These are negative Qs. And that's what I talked about in the videos. Another type of reaction that does the same thing but has a positive Q. So if it has a positive Q, it should want to run on its own. But it doesn't. Why not? Well, it doesn't run on its own because the nuclear force may want to run on its own if you put these nuclei really close together. But while they're coming in close to each other, the Coulomb force is going to repel them. And the nuclear force only acts for 2 Fermis. So if you just put a couple of nuclei, like an oxygen and a proton or something near each other, or even this one, which has a positive Q, if you put this proton next to this nitrogen, or hydrogen, nitrogen gas, they do not start nuclear reactions. The nuclei can't get close enough. They'll never interact. You've got to squeeze them together. And there's a lot of ways to squeeze them together. On this planet, we throw them. And smack them together. So even though they're being repelled by their Coulomb force, if I throw them hard enough, I can just overrun that Coulomb force till they get close enough, the nuclear force takes off and I get the reaction. In the sun, gravity squeezes them. It pulls in, and as it does and compresses that gas gets hot, it gets energetic, and it's just like me shooting with the accelerator. It's got enough energy to overcome that Coulomb force and smack together. Now, creating a sun on planet Earth is a bigger challenge. That's the challenge of fusion we want to talk about a little bit. All right? But they won't just do it on their own, even if they have a positive Q, because they can't get close enough. If the nuclear force was long range, this would work. This is not what happened. Of course, if the Coulomb force was long range, and you walk next to a cup of water, your nuclei would suddenly go into nuclear reactions, and you would annihilate the planet. So fortunately, that does not happen. Okay? So, these guys won't run because they won't even run if you put them close together unless you give them energy. Even if the Q is positive, they won't run unless you can smack them together close enough to overcome the coolant force. So let's look at another type of reaction like what I just talked about. This one is for Q greater than 0, but I'm going to choose a very special one called resonance reaction. Resonance reactions are extremely useful in engineering applications. They can be used for material science, they can be used for analysis. Their advantage is that they enable you to profile materials, single atoms at a time, without destroying the material. So you want to find if you have hydrogen in material. Why? Hydrogen will cause a metal to embrittle, it will cause the metal to fatigue and fail. And you're building an airplane wing or you're building a gun barrel. If that thing fatigues and fails, it will not perform properly. There is hydrogen in the air because there's water vapor in the air. No matter how hard you try, you have got hydrogen in your sample. Therefore, you will have to process that hydrogen out. Problem is, almost no analytical technique in the world is able to detect hydrogen at parts per million type concentrations, and yet we know that it affects metals. I mean, this is an extremely important problem in metals. The titanic steel was the best steel ever made. They spared no expense. That steel is weaker than a dog chain bought at Walmart today because the steel had impurities in it. Material science is an incredibly important field for an engineer. And the study in how to apply these techniques is an essential tool if you want to work in the modern future. We're not going to be in the old days of the steel industry of Carnegie of 1800s. Those days are over. We are building materials one atom at a time with modern physics. You can't do it, you can't compete for these type of jobs. So what they do with this stuff is they want something that when you shoot a beam at the particle, only if it has exactly the right energy will it create one of these reactions and emit probably some form of a gamma ray that you can detect. So if there's none of this nitrogen here, then you'll never get this gamma. And if there's nitrogen right at the surface at a very particular energy, so as to distinguish it from anything else, you will get this gamma. And the number of gammas will tell you how many nitrogen are there. And then what you can do is turn the energy up. The material will no longer interact with the nitrogen at the surface, but as it goes into the material, it will slow down. And at some depth, it will be at the right energy, and you'll be able to measure the nitrogen at that depth. So just by turning up the machine, you can profile step by step single atomic layers of nitrogen throughout the material. That means that you can know where it's at. You also can shoot nitrogen into the material and make materials single atomic layers at a time for any purpose with any characteristic you would like. Combine those two together, and you have real power in an engineering application. This leads to dopant in the semiconductor industry. It's how we make all of our computer chips. All right, so we would like a material that has a resonance, that is, only interacts at a very narrow energy range, and then we can use it for profiling. So let me show you how you do. First thing you got to do is you got to think about the Q value. So I've got, for instance, a particular reaction, which is this reaction. That's why I chose it. But I'm going to shoot the nitrogen into the proton, in this case, in order to measure hydrogen. So now there's a slight error, and then there should be a minus sign different. I don't have these guys. My Q should have a minus different. These guys should be subtracting it, the oxygen, but the numbers are right. If you look at this reaction and work through it, 12.128 MeV of energy is created from the reduction of mass. That's a positive Q value. So you might think, just put them together and it will run. Slight problem. This particular nucleus has widely spaced energy levels. So you can't just form the compound nucleus unless you can form it in one of those states. And the Q value puts you here, and there's not a state there. So it's not allowed. Now, what I mean by not allowed, it's highly unlikely. Okay? You need to give it a little bit more energy to raise it to here. So you can figure out 2.53 MeV of energy, and this is what the Q gave you, 12.128. So the difference in this is how much energy you need to give it to raise that compound nucleus to a correct state, and then the reaction will occur. Now, there's a little more to it. You got to conserve momentum when you hit these things. So it turns out that only 15 over 16, we threw the 15 at it. 15 over 6, I'm sorry, threw a proton at it in this case. So the target divided by the total, 15/16 of the kinetic energy, will go to give you this energy difference here. If you threw the nitrogen at the hydrogen, then this would be 1/16. You need a much bigger machine to make that happen. Let me show you what happens in terms of this is the probability that it occurs. Notice this is a log scale. So right here, there's almost no probability, and then this thing jumps by almost 4 orders of magnitude. So it is 10,000 times more likely to occur at this energy than it is at this energy or this energy. So you're only going to see those nitrogen molecules right there at the surface, and only if you throw this much energy. Now, if you throw less than this, you'll be over here. You won't get any. If you throw more, you won't see any surface, guys, unless you slow down to this place right here. So you throw exactly the right amount, you measure the nitrogen right here. You throw a little bit more. If you throw too little, it doesn't measure anything. If you throw too much, it goes clean through the material. If you throw this much, it will come in, slow down to 6.38, and this little layer right here is the only nitrogen you'll detect. You catch those gammas, and you know that layer. So just by turning up the machine slowly, step by step, you can individually slice it, but you've not actually removed any atoms. So you can take this sample when you're done and then go use it for anything else you want, because you've done no damage to it. You've just been able to peel it nuclear-wise without actually peeling it off like you would in chemistry. Now, if you can determine that hydrogen's somewhere in the sample, in chemistry, you just take the sample, dissolve it all, and you can say somewhere in the sample there's hydrogen. I'm talking about measuring hydrogen at single atom depths and giving you an information step by step. Yeah.
What are you actually shooting at them?
In this case, I would be shooting, if I'm looking for a nitrogen, I'd be shooting the hydrogen.
Okay.
If I want to reverse the process and look for nitrogen, which is really what I would have done at this particular energy, then if I'm looking for hydrogen, I'd shoot the nitrogen 15.
Is it difficult to accelerate nitrogen 15?
No. It's a little bit difficult to get nitrogen 15 out of an accelerator. In a gas, you can do it pretty easily. In a solid form, it's not quite. And the reason is that if you've got a tandem accelerator that needs negative ions, nitrogen has 0 electron affinity, it won't form a negative ion. So you have to send a molecule and split it. But if you've got a positive ion, that's something that sends positive particles, all guys pretty much you can rip an electron off. We had to send negative ones, so I had to build a special machine and a special system with my students for the Army in order to be able to do their stuff. But this is how they analyze all of the gun barrel material. You can do the same thing for lots of other stuff. We've dated fluorine inside of arrowheads to get the date and chronological. We've used this technique to study, for instance, art forgeries. This is standard engineering technology. One of the tricky parts of nuclear reactions is they're all special, they're all different. You have to write your own software, you have to work out your own math. Nobody can do it for you. There's no commercial application you can buy. So if you can't do the stuff yourself, you can't compete, your company's out. All right? This isn't like RBS or some other stuff where anybody. But the good news is, you have to do it yourself. Because quite frankly, if it's commercial, I don't need an engineer. Hire me an electric. I can buy one of George's groups, so they're a whole lot cheaper, and they can use the same computer software to get all the data that you can, and I don't have to pay them over $40K. So if you want to be able to be employed, you've got to be able to do something that I can't do with a DeVry graduate or a technology graduate. And here's an example of something you can't do. Right? This actually requires you to have a lot better training. You just can't do these canned. And that's true of a lot of other applications in engineering. This is just one of them. All right. So that's one type of reaction that has a lot of uses, is resonance reactions, okay? There's one other type of nuclear reaction that shows up occasionally called stripping reaction. I don't find stripping reactions to have nearly the applications from an engineering standpoint, but they're useful from a physicist standpoint. So if you're looking, to do something as an engineer, probably not going to find that many applications of stripping, but if you want to be a physicist, there are. These kind of are ones where you send the proton in, and you hit something, could be anything, I don't know, an oxygen 16. And it's energetic enough that it doesn't form a compound nucleus. And instead, it'll knock something preferentially like out this way. And it could be, for instance, a deuteron. So in this case, it took 2 neutrons and the proton back. And coming out this way would be an oxygen 15. How we know this reaction occurs? It won't show up in the back. It's very, very sensitive to how you shoot this in. At what angle you shoot this in, what the energy that you shoot this in. So it's almost like billiard balls. One billiard ball comes in, it knocks another billiard ball out the other end. It might knock a proton out the other end. It might knock a neutron out the other end. So a lot of these reactions are what are called PD reactions, proton in, deuteron out, or they're often PN reactions, proton in, neutron out. So you've got a way now to produce neutrons if you want to build a neutron generator. And in that is one application engineering-wise that people do a lot of. Neutron tomography that's used to analyze steel. They'll have an accelerator over there with a smaller one, usually Cockcroft-Walton, with a lot of energy. There's a company in Pflugerville, Texas, Texas Nuclear, that builds these things for commercial applications in steels and others. In aerospace, they shoot protons in, they knock neutrons out, and then the neutrons are used as a probe to study and analyze the steel manufacturing in real time. So as the steel comes by, they're actually imaging it, just like you would image it with a camera. Yeah?
Does this type of reaction have anything to do with P and N-type semiconductors, or is that something?
No, it's totally different. A P semiconductor, you put an element that is out of a group group 3, so it's missing one electron. It's neutral, but it has one less electron needed to bind with the 4 silicons. So it's got a free spot that electrons can jump into. That's called a hole. And then N is a group 5 semiconductor, like arsenic, and it has too many. So it's got one electron that's almost not even bound. And that electron's free, like a Mexican jumping bean, to jump between atoms. Okay. So you give it a little bit of charge, and either the hole will move, or this electron will move, and it creates the current.
Gotcha.
All right, so threshold reactions, stripping reactions, resonance reactions. There are other types of reactions, but only a nuclear physicist who's going to be a PhD specialist would know. These 3 are the ones that potentially could show up the most in your orbital work. Stars. Well, stars are an application of nuclear physics. In one way or another, everything in our universe that we know about comes from stars. They are the source of all energy. They are what warms our planets and makes our weather and generates our gasoline and makes for coal. They are what makes all the atoms that are in your body. So everything that's matter or energy on this planet, one way or another, is related to nuclear physics. All right, so the question is, well, how do you know about that? Well, we know a lot. We know how the universe started. We know what the reactions were. We know how stars live. We can predict how long they live. We can find their gravity. We spend a lot of time in nuclear physics studying the nature of the nucleus. So stars work off fusion, which is not the same thing as fission. Fusion is when you fuse together or push together two lighter nuclei to make a heavier nuclei. So at the beginning of the Big Bang, you have some electrons out there, you got some neutrons out there, and you got some protons. Protons collect as time goes on with the electrons, and you get hydrogen gas, which is what forms most of the universe. The hydrogen gas is a sufficient enough density, will get enough gravity that will actually pull it together. Because it wants to conserve angular momentum, since gravity provides no torque, its natural collection is to form either disks, like galaxies, or to form spheres, like stars. When you take these light nuclei and you push them together under gravitational pressure, then you're going to get them close enough that they can interact. And if they have a positive Q reaction, and they're close enough together, they'll start undergoing nuclear reactions. Now the problem is, you get them energetic enough so you have a good probability to interact. So you get them pressed in high enough density to have some probability of acting, because each one of these reactions may be very low probability, but if you have enough of them, you're going to get something to run. And to confine it together. It doesn't fly apart, it stays close together. We'll come back to that because that's important in what's known as the Lawson criteria to build a fusion generator on planet Earth. The reason these guys work the way they do is because as you go along this binding pernucleon curve toward iron, if you do that, you keep raising this thing up, which means that you're deepening the well, which means you're giving off energy. Nature wants to minimize energy. But there are some jumps. For instance, there's a jump around nucleon 5, there's a jump around nucleon 8. And that means that there are places where if you tried to form these together, it would not form a positive Q value. It would actually take energy. So there are certain reactions that can occur when the star has to avoid. So I want to move up the binding energy curve, but I got to realize that some reactions aren't allowed because they'd be blocked from high Q. And all of that I've already given you previously in your notes, so you shouldn't really need to write much down. So move up the binding area curve means the nucleons fall into G per, well, they give off energy. That's just what I got through saying a minute ago. Now, you don't need to write this down, but at least I want to talk about it, how a star burns. So inside the star, we're talking about a young star, like the Earth. Or not the Earth, I'm sorry, the Sun. Our Sun. Yeah, that's right. The Earth does not have sufficient gravity to be a star. You've got a proton and a proton. Okay? If the proton and the proton get close enough together, they can form a deuteron, positron, and a neutrino. Now, if you look at that thing, this thing looks a lot like beta plus decay. Okay? You know, beta plus decay, you've got this thing that you want to reduce the number of protons by converting a neutron. What's proton, neutron, and this sort of stuff. Where you converted that proton into a neutron. So it looks like a proton added to a beta plus decay. And if you do that, that actually generates energy. Great. Then this deuteron manages to find another proton. And it forms helium-3 and a gamma. It gives off some more energy. I need that to happen twice. I need it to happen twice so that I'll have 2 of these helium-3 atoms sitting around. Because if I take 2 of those helium-3s together, They can form together to form an alpha particle, which is very tightly bound, and 2 protons. Why I need 2 protons back, 2 hydrogens? Because I want to put it back into the system and refuel. So at the end, I get back what I started with. But I've gotten an alpha particle, and I made some changes. Now you've got to count everything up. I got 2 back, but I started with so many. Go through the whole calculation, and what you find out is 4 protons become an alpha, 2 positrons, 2 neutrinos, and 2 gammas. Cancel out all the, you add this, you subtract that, you go through all the steps. 4 protons and now become an alpha. So I had a hydrogen star, and I'm now converting it to a helium star. And later on, the helium star can be converted to other things. So I can actually start moving and getting heavier elements. This is how the heavier elements are formed. Okay. Now, if you take that and you calculate the Q value, I'll remind you a couple things. Let me put that back up here so I count all this up. So I got the 4 protons, there you go. But remember, we don't like to work with protons because that's not what we have. What we have is atomic masses, right? So you got some extra electrons there, 4 of them. Then you've got this alpha particle, that's 2. But you remember you also created this positron. So when you calculate these guys up, you do all the calculations, they'll work out right. Multiply by 931.5 and you find that you get 26.7 MeV of energy by this process. That's a lot of energy. Yeah.
Are neutrinos massless?
The neutrinos are, for all intents and purposes, massless in terms of these energies. Are they totally massless? That's an argument. I think they believe now that they have some potentially very, very finite mass, but it's incredibly small. So you don't need to do any Q value calculations. Only when you consider the total number of neutrinos in the universe may the mass not be unimportant. It's kind of like a penny really doesn't matter, but if you had a quadrillion pennies, you might should consider it. But you don't need to do it for Bill Gates' bank account. So this thing has a lot of energy, and that's what fuels. Now what does that energy do? One of the other things, it presses the gas outward. Okay? So the gas pushes outward, the gravity pushes inward, and those 2 forces are balanced. The outward push in E&M is called radiation pressure. So the pressure, force per area going outward, is canceled by the gravitation as long as this reaction runs. So the star has a fixed size. Its mass is getting less all the time. It's burning up energy and giving energy off. That energy comes to us. A plant absorbs that energy, and then you can get that back in terms of gasoline or whatever. But it got that energy originally from this nuclear reaction. And it also made heavier elements. Now what happens when that reaction runs out? When that reaction runs out and helium begins to dominate, it's going to start a new reaction. A helium reaction. That helium reaction is more energetic than this reaction. So when that happens, the star is suddenly going to have a bigger outward push than an inward push. And it's going to expand to what's called a red giant. It basically is going to swallow everything up, I think, past Mars. So at that point, we will definitely be inside a star. However, when that happens, I'm not really worried about it. My stent's going to get me before then. So maybe you have to worry. I used to think I was invincible since there's no evidence to the contrary. But I now begin to believe I will correct long before this happens. And that reaction will go for a while until, again, it will actually cease and drop back down to a white dwarf. It gets enough energy to start another. That's where ours is going to stop. It'll burn at a white dwarf at higher reactions and then basically burn out and become what's called a black dwarf, where it won't have the energy to continue doing others. There are other possible type of stellar processes. Some have a lot of carbon in them, probably because, again, they came from other dead stars that had created the carbon. And they can run what's called a carbon cycle, which is even more complicated. You get a carbon and a proton. From hydrogen, you form a nitrogen-13 and a gamma. The nitrogen-13 then breaks down by beta decay. Then the carbon-13 interacts with the hydrogen, becomes nitrogen-14. The nitrogen 14 acts with the hydrogen, becomes an oxygen 15. The oxygen 15 then breaks down to nitrogen 15. Nitrogen 15 adds that, and you get carbon 12 back. And if you go through that whole reaction, you'll find that it's even more energetic. Point being is, because we got nuclear accelerators, we've been able to measure the cross-section probability and energy of all these processes. And so an accelerator can be used as a time machine, but it also can be used as a way to study things you can't get into, like how to go to the sun and understand what's going on in the sun. You know, the statement says, the Aggie says, but we're going to go to the sun. And Russian Americans said, you can't do that. He said, oh, we're going tonight. No, but we can tell you what's going in the sun because we know the laws of gravity, we know spectroscopy, so we can look at the element compositions, and we know cross-sections from nuclear physics. So we have figured out ways to, in essence, do laboratory experiments in the sun without going to the sun. We're very tricky. Right? We're good at solving problems. So, small stars form heavier elements, and as they form these heavier elements, over time, they eventually move toward iron. Now, when you get to iron, the problem is you can't get any heavier than iron from that. So what you have to do is you have to go through the shake process. And this occurs because you can actually get the star so compressed that you actually can end almost basically with just a bunch of neutrons. And these extra neutrons can go into the material and create things that are not stable, and then they can decay into other elements. And this is how you start forming up the heavier elements. So Hans Bethe did the first part of this. Willie Fowler and his group at Caltech did the later start of nucleosynthesis. So older stars, after a star uses up hydrogen, it begins using helium and other nuclei. The new heavier nuclei continue till they get to iron, like I said. But even heavier elements are then made by neutron capture, followed by beta decay, until you get to about bismuth 209. After that, the probabilities are not good that you're going to go beyond it. So how do you get uranium? Well, you need an exploding star. It's got a huge amount of neutrons and such go through it. These are known as supernovas. They don't happen very often, and that's why those elements are very rare. Right. So, guess what? You truly are a star. You are made of stardust. And to dust someday you shall return. So before you get the big head, Giovanni, you're from a dead star.
Oh.
Okay, so you're not able to sing and dance, we know, and you're not going to be a star on American Idol, but you are really made from stardust. You were formed inside, all your elements were formed inside the star itself.
For a minute, I thought you were giving me a compliment.
Oh no, I can't do that. My job is not to do that.
I was flattering myself.
That would cause you to have a heart attack, and I don't want to do that.
True. I'm like, oh my gosh, is this really happening?
Anyway, this is how stars work. The great news about these is these reactions are much more energetic and produce a lot more energy in a cube than do fission reactors in nuclear power plants. And they produce these things like iron in stuff that's stable, so you wouldn't have any spent fuel rods that you need to store. So this would be a great way to produce power. This is how power comes to us from the sun anyway. The problem is the temperatures and the heating and such are not normal on this planet. So how to make a mini star on this planet to solve our energy crisis? And that's what fusion reactors are all about. This is why the government wants to spend money on them. And ever since I can remember, they've told me that it's about 25 years from now. And the reason for that is that physicists tell you that say, how long is it going to take to build a fusion reactor? They say, no idea. I mean, we don't know the physics involved yet to be able to solve a fusion reactor and build it on planet Earth. And a congressman or senator says, oh, but you know, how long? You can't say you don't know. You have to give a number in Congress. So the answer to that is 25 years. Why 25? Senators are in power 4 terms. Would be 4 times 6, 6-year terms. Well, hell, that's a lifetime. So that means beyond my lifetime, 25 years. All right? Of course, 25 years later, they say, why did you lie to us and not give it to us? We said we have no idea. So today, it's 25 years, because we still don't know how to do this. But if we solve it, it would be the single, maybe most important thing that we could solve. How to fund energy and food for our fellow people for the rest of their lives and not have these radioactive environmental problems. Gotcha.
Is the same like a hydrogen bomb? Is that the same
A
company?
hydrogen bomb,
Is that-
you
how's that
put
different?
the hydrogen around a regular thermonuclear warhead, a regular atomic bomb, I should say, and then when it goes off, it gives the energy necessary to start the hydrogen to fuse, and that's what ramps up the energy. It used to be called a super,
Right.
because it's just an increase.
Okay.
It came from a study where people were concerned that there is hydrogen in the atmosphere, and they were afraid that setting off the bomb might set off the atmosphere and wipe us out. So it originally started as make sure we don't kill ourselves. And then they said, well, it didn't work. We won't kill ourselves. Why won't we kill ourselves? Well, it's not dense enough. It doesn't. Well, that means that if I made it more dense, you can see how physicists take whatever the problem is and they start turning it around. I'm reading Teller's biography. It's rather interesting thing. His first peace activist, and he became the father of the hydrogen bomb. Fusion power. The advantage of fusion power is it's more efficient, like I said, so you get more energy per kilogram of fuel, so that's nice. It's got an abundant source. Okay, you can get deuterium out of ocean water, and we got a lot of ocean water. So we got ready-made stuff of supply of fuel. We don't have to look for enriched uranium or something like that. It's already there, easy to get. And it has less environmental impact because this produces these long-lived radioisotopes that you got to figure out what to do with. It produces like water and such. Okay, so the net effect is, if you could run this, you'd be able to have an energy source without bad things. If. All right, that's why every federal government's done. Problem, it is technologically very difficult. That's like the understatement of the century. But I won't say impossible because, you know, you say impossible is that if you can no more do that, then go into the moon. We've been to the moon. All right, so.
It's like 25
Someday,
years. So.
25 years from now. I will do it in a decade. Why is that? Because president's only elected for 8 years. You notice the deadline was after Kennedy would be out of office. All right, so politicians always select deadlines beyond their own term. They can take credit if it happens, just beyond them, but if it doesn't happen, they can blame it on the other party. Good idea about politics. So it is very difficult, and we're trying with a couple of initiatives right now to actually be able to do this, but we're still not having success yet. We know what reactions to try. There are 3 reactions that can be used. You can put deuterium and deuterium together, and if it's hot and it's pressed down in nice temperature, and we get the deuterium from the salt water, it'll produce tritium, which is a radioactive isotope, and it'll produce proton, and you'll get 4 MeV of energy out. That don't seem like much of a to me. I like a little bit more kick out of my fuel. Okay? Well, we can take deuterium and deuterium, and they can form helium-3 and a neutron, and you get 3.3 MeV out. So both of these reactions would actually occur in the same reactor. But the one that everybody always talks about is the savior of man reactor. You take deuterium and tritium, you get an alpha and a neutron, you get 17.6 MeV of energy out, which is just a little bit better kick than these other guys. So this is the one they're always working on. They either got a tritium shell or they have a deuterium pellet and they smack it with a laser. However they're doing, they're trying to drive this reaction and make this thing work.
Is this primarily because we have an abundance of deuterium? That's why we're looking at
We have a lot of deuterium, and besides that, it simply has better kicks than does, for instance, hydrogen. Helium could be done, but there's several problems with basically keeping helium gas around and actually getting it pressed. It is easiest to work in a nuclear problem where you have the fewest number of nuclei, so you need the less knowledge about how the nuclear force works. If you got this to run, then maybe you'd understand how to run the helium reaction well.
If we got this to run, would we be creating helium?
Yes.
So would that help with the helium shortage that I've heard rumors about?
What helium shortage?
I heard them. So.
I don't believe in any damn helium shortage in the world. We got helium stockpiles up there in Pentax and in North Texas, right and left. They're getting rid of some of it. The federal government, I remember Kennedy was complaining, you know, that we were keeping it for blimps. We're not keeping it for blimps. The reason that we have that stuff up there is that it comes from radioactive decay, and we don't want people to know how much we have, because they knew how much we have. They know how much uranium and reactive fissionable material we have. We don't want to tell people how much material we have. But that's it. Helium will naturally go up in the air, so the only way to get helium is to drill it with a well. because it's formed with the uranium or a alpha emitter, and it emits in the rock, and then the rock picks up electrons to the alpha and becomes helium, and it's trapped in the rock. If it's above the ground, it floats into outer space. So when you have those helium balloons, you let them go, they go fly off.
Is that what they're going to do with North Korea to find out if they have?
No, North Korea's not doing that. North Korea's looking at trying to enrich uranium-235.
Okay.
They're making atomic bombs. And I know of some ways that we're trying to build ways to look over your borders and do things, that's what you're not allowed to know. So let's assume that I want to make a mini star on Earth. Well, if you want to make a mini star on Earth, there's basically three things that you have to do. One is you got to get high temperature. The reason you need high temperature energy is, remember I said these things have a Coulomb barrier. So if these particles don't collide at really high speed, there'll be no probability you can tunnel in and begin to interact via the strong force. So if it's low, it just bounces back, you get no reaction, you get no energy. So you got to get the temperature high enough. Now we can't build it as hot as a star. That's just not going to be possible. We don't have gravitational pressure and such. But we do need to make energy. Now we have accelerators that can put energy. We can put electromagnetic fields and cause it to heat, just like you heat an oven. There are ways to pump energy in. But we need to pump as much energy in, and then we want the reaction to run, and when the reaction runs, we want to give enough energy to keep it heated and take the difference, the extra energy, off for electricity and power. That's the goal. Another thing you need is, it doesn't do you any good to have a prime probability that this particle goes through if there are no particles hitting. All right, so you need to have a lot of the particles close together. You need to have a high density. This is given the symbol eta, and if you don't have that, it's not going to work either. And the third thing is, maybe you got a good temperature so you have a probability that it works. And you have a high density so it actually reacts. But then it blows itself apart so the density goes to zero and it quits. Well, that's okay if you build bombs, but if you want to build a power plant, this thing has to keep running non-stop. So that means you got to confine this thing so these guys keep banging on each other and keep generating energy. So there are three things you got to have, and you can play with each one. You can either build more temperature or more density, but most importantly, they got to be confined. So usually what's done is the temperature we can get. It's these two. You can either have higher density but lower time, or greater time and lower density, and if you get it just right, you can make this thing run. There was a guy by the name of Lawson who figured out what that requirement was, and consequently it's called the Lawson criteria. If Jaden had done it, we'd call it the Jaden criteria, but he didn't do anything, so he doesn't have anything named after him.
Good job, Jane.
So the Lawson criteria states the following. In order for you to break even, that is, to get more energy out than you put in and sustain the reaction. So you may hear that sometimes they talk about breaking even, but they break even for a microsecond. And then it fails to meet the criteria. You must keep this criteria. The density times the confinement has to be greater than 10 to the 14 seconds per cubic centimeter. So if this was 10 to the 14th and this was 5, that would be good. Or if this was 5 nuclei per centimeter cubed and you could hold it 10 to the 14 seconds, that would work. I don't know anybody's going to achieve that. So what people have done, they come up with two ideas. One says we're going to make this really high, but this is going to be short. This is where they shoot the lasers and they try to compress it. And the other one says, no, that seems difficult. We're going to make this low, but we're going to keep it going around a long time. These are called tokamaks. So these are the two possible ways that we can do it. But that's what we're trying to do. We know exactly what we got to make. We just have to be able to do it. Here's a tokamak. So in a tokamak, you have two fields. One field goes around the circle of the donut, if you will. Now, my problem is they're going to have this gas at a temperature like a star. If you put that gas next to that metal, it's going to vaporize it. So I've got to put this in something that's evacuated, clean, and then I have to use fields to hold it like a bottle. I can't let it touch the walls. This is a real problem, because even though the walls don't touch, they still get hot, they spit crap into your system, which causes you to poison it. So that's one thing you have to work on, is making better walls. But they put a magnetic field like this, and if you try to get away from that field, what happens is it applies a force and pushes you back in the middle. In addition, these currents, when you have a current, you have a magnetic field. They're producing magnetic fields like this, like a wire. Those two fields, this is called the poloidal field from the current, and this field, the axial field, combine to make a bottle. It's as if it's a thermos. And the gas is held in that bottle. Outside of here is some sort of metal that's holding this whole damn thing together. But it's actually held inside that magnetic bottle. And then we pump energy. And how do we pump energy? Now we can inject with the accelerator some energy in the plasma. The alphas that come out of the nuclear reaction bang into things. That's heating. We also could just hook up like an electromagnetic field like you do in a power supply and just send current, and the current's I squared R, and it can heat. We do all three. So we pump energy in this, we get it hotter, 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 wait for it to react, and then it cools off. It forms kinks in the middle, whirlpools. Then for some reason just radiate energy like crazy and become cold spots, and we don't know why. Because we don't understand plasma physics well enough. So we jack up the energy, and then it'll stop. And then they'll figure out how to get around that, and get that kink to go away. And they'll start jacking up, and they'll go up, and they'll find another damn mechanism by which it comes the energy. And they continually have this problem. Now for like 50 years. Yeah.
Where is this?
Well, there used to be one at UT and Oxford, but the main one for inside the U.S. right now is at Princeton Plasma Lab. You can go on the website, you can find their website. Tell you all about it. You can even play Keep the Reactor Running. I was trying to do that last night. It was not being very successful. It's better than Chris was, but I was not being very successful. Its characteristics is it's got a reasonable set of energy and temperature. It's got a very low density. And look how long these confinements are. It only keeps these particles near each other a tenth to 10 seconds. Okay? So either they need to get the density up, which they haven't been able to do, or more importantly for them, they need to keep this heating longer. All right? They need to keep it longer. Next time I'll talk a little bit about how we're using lasers at Livermore to try to crush the pellets and to get the temperature up. One of the advantages that they have is in the process of creating that plasma, it's similar to what happens in a nuclear bomb. So in essence, it's also nuclear bomb tested. That's why we don't believe in anybody should do any type of above ground or underground testing, because we're environmentalists. It's also because we're the only one who can test bombs. All right, because we have our own bomb testing system. All right, for our stewardship program. And I'll talk about that next time, and we'll finish up this month. See you guys later.